So what the hydrogel technology does, that EDYSTON, when you spray it in the concrete crack, over time it starts curing into this hardened gel that's not going to allow the transmission of that chloride. Another thing is where we find that here in Colorado we have a lot of issues with alkali silica reactivity, and it's not normally by itself. You know, years ago I wrote a paper to be published in Concrete International. And I remember one of the editors, I had put in the paper that alkali silica reactivity was the primary cause for concrete failure. And I remember one of the editors, who's a good buddy now, but one of the editors said that they wouldn't accept the paper if I had this, you know, this clause in there that said that ASR was the primary mechanism for concrete failure, which normally it's not. And that's the case here in Colorado. We oftentimes see ASR lead to something else, or something else damaging the concrete, and we see, because of that damage, the ASR is exacerbated. And what ASR is, for those of you who don't know, ASR is the aggregate sensitivity to the alkaline environment of the hydrated cement matrix, and that sensitivity manifests in the form of this expansive gel. And you know, here in Colorado we have a lot of aggregate that is sensitive to ASR. There's a lot of potential for it, and as it turns out, the hydrated cement matrix, it's an alkali infested environment. I mean, whether or not you replace your Portland cement, you know, a type 1,2 with a type 1L, you might have some lower alkali contents. And even with replacing the cement material with a supplementary cementitious material like a class F fly ash, you'll find that some of these SCMs will have a higher alkali content than the cementitious. And then of course there's the alkalis, or the cement. Then of course there's the alkalis that can come from the soil, from the water. Anytime these alkalis are present, as they are at the interfacial zone between the coarse aggregate, which is a silica, a form of silica, and I believe it's the tetrahedral form. The alkali at that interface, the cementitious at that interface, which locks in and almost acts as a hard candy shell. As we get closer to that interfacial zone, we hit something called the wall effect, where, especially with coarse aggregate, or crushed or manufactured aggregate that has a higher surface area to it, we find that the amount of paste that is needed to lock in that aggregate at that interfacial zone between the coarse and fine aggregate and the hydrated cementitious matrix increases because of the amount of surface area. But it just doesn't work out that way. We actually see a decrease in paste the closer we get to that that aggregate interface, compared to the further away that we get into the body of the concrete. We just have less paste at that interfacial zone. And I believe that was talked about by A.M. Neville in his book, Properties of Concrete. And I think they're up to like the 15th edition now. And if you're looking in the 300s, it's either page 317 or 367, where they talk about this wall effect, and they have a beautiful representation of an aggregate with the microscopic asperities from its either crushing or whatever type of manufacturing, or just its natural state, but what causes that wall effect and that increase in specific surface area. So we already have a weakened area at that interfacial zone between the aggregate and the hydrated cement matrix. So there is area for this ASR, this alkali silica reactivity gel, to thrive and survive, and for it to start growing. And what it ends up doing is it grows in to fill up that space in the interfacial zone as an immature gel. And then as it dehydrates out the environment, it becomes an old, less elastic, mature gel until more of the water and alkalis are present. And this doesn't happen this doesn't happen sequentially. This happens, you know, at different events or different ages based on the relative humidity and the available alkalis and reactive silica at that localized environment. But still, just the same, as that gel continues on to grow, if we assume that it's happening the same time at the same rate around the entire aggregate, what we find is that as the gel starts hardening, it creates another confinement zone. And as we get more of the, when you look at the gel, it has a fibro-like, wispy-like morphology with a lot of needle-like phases that are intertwined together to create very fine capillaries, which have a tendency of imbibing and drawing in water. And in doing so, it's a vicious cycle. We bring more of these alkalis to the ITZ, more of this moisture. You still have reactive aggregates, so we start creating more of this immature gel within this mature gel, and it starts packing in our interfacial zone and filling in the pores and cracks, and keeps on expanding until the point we create those same type of residual forces in this confinement zone. And those residual forces from the swelling overcomes the shear and tensile capacity of our hydrated cement matrix. And in a lot of cases, it overcomes that of the aggregate. And what you end up seeing is this breaking down of the concrete at the interfacial zone, and oftentimes through the aggregate. And as we start cracking from within the concrete here, it starts leading out. Remember, concrete is very rigid and brittle material, and it doesn't like any type of movement, especially internal expansion. And the test that we use to identify that is an expansion test, either ASTMC 1293, 1260, 1567, and then there's these rapid tests too that have recently come out. What we find with both of these failure mechanisms is that when we approach them, and you can see this, and we have a wonderful book out called The ABCs of ASR, which I believe is like 15 or 20 bucks, the electronic version on Blurb. And it shows these gorgeous pictures of concrete that has failed to either ASR or calcium oxychloride formation. And it's a very telltale sign. It has very specific types of cracks that have, leachating or leaching of salts that come out of them, whether those salts are white or yellow, or you also have a reddish hue to it or brownish hue if there's a combination of moisture, salt, and steel corrosion. And with this hydrogel technology, it works excessively well with deteriorated concrete. And what would be an obstacle now becomes an opportunity. So while we don't have time to get into today, what I wanted to really focus on today was an introduction of what the purpose of our live events are. With EDYSTON, our concrete technology specifically designed to be a solution to this deteriorated concrete, the least talked about problem in the concrete industry. And for my carbon negative and my carbon neutral folks out here, you can't get any more carbon negative than this. I mean, what's more carbon negative than saving the concrete that we already have in place? I mean, every time you have to break down concrete and replace it, there is a carbon footprint for ripping it out, crushing it down, putting in a landfill, and that landfill cost, that carbon footprint, is a legacy cost. And then, of course, it's replacing it, getting the raw materials, getting the transportation, and so on and so forth for building a new concrete structure. So if we can get another 5-10 years out of our concrete structures, give them more life, rejuvenate them, then that creates a carbon negative environment where we don't have to rip that stuff out. We've actually kept that stuff in place, and now that what would be spent, we can use that somewhere else. So it's negative on that point. What we also find with this hydrogel technology and the technology that we're bringing out to the industry is that it's very easy to use to make a global impact. So it's not only the carbon negative local, and this can be used for homeowners, but we're also talking about the commercial industry on a very large front. It doesn't require any special training. It just requires some little attention, and the technology is easily placed. So the technology that I've talked about, I've mentioned it a bunch of times. It creates this hydrogel and concrete, and I wanted to give you not only the textbook definition of it, which I love discussing these things, and if anybody is curious for some more to literature and reference information, we can get that to you. But I wanted to focus on how that technology can help out concrete in two very specific ways. And we talked about the physical and chemical breakdown of calcium oxychloride formation and alkali silica reactivity. So if you have those issues, check those out on our website. We've got some examples, and try EDYSTON out today to help get 5 to 10 more years out of your concrete, rejuvenate it, bring that concrete back to life. So thanks for joining us today. Let us know if you have any concrete questions, concrete concerns. Have an awesome day, y'all.